Welcome back to the workshop. We want to continue taking a look at section 5.4, rooted trees. And in this video, we want to take a look at a theorem and a definition. The theorem just deals with some things that we already know about trees that we want to adapt for rooted trees. And then the definition gives us some language that we use with rooted trees. So it's actually very nice. Should all make pretty quick sense. So no worries there. But in the rooted tree, the theorem or the things that we know about a tree that we want to bring over are the number of edges. So in a tree, there is one less edge than there are vertices. And that's going to stay true in a rooted tree because when we ignore the directions, what we have is a tree. So, okay, so there's going to be one less edge than there are vertices. Makes sense. The other thing is that since there's no cycles in a regular tree, there are no directed cycles in the rooted tree. No cycles in a regular tree, so there are no directed cycles in a rooted tree. Makes sense. Because when I ignore those edges, I need there to be when I ignore the directions, I need there to be no cycles. So there's still no cycles, directed or not, okay? And then the other thing is that in a tree, there is a simple path from each vertex to every other vertex. Now, because we can't travel edges backwards, what we end up with is a slight adaptation. We end up that we can move from the root to any other vertex, but that's it. So there is a unique, simple, directed path from the root to every other vertex or to each of the vertices. So let's take a look at our notes just to see that. So this theorem is exactly what we just said. The number of vertices is one more than the number of edges. We said it the other way, that's fine. That the number of edges is one less than the number of vertices. There are no directed cycles, of course, because when we ignore the directions, there are no cycles. So if there were a directed cycle, then ignoring the edges, ignoring the directions of the edges, there would of course be a cycle, and that would be a problem. So there can't be any directed cycles. And then there is a unique, simple, directed path from the root to every other vertex. And just to make sense of this, right? If we look at a tree, if this were not a rooted tree, if this were just a tree, we could travel from H to E to anywhere else, from A to E to anywhere else, from F to E to anywhere else, and that's fine. But when we have the directions, we can't move up these, right? We can't move up these branches or these roots. All we can do is move down. So we can travel from E to anywhere else. We still have that part of it, but we can no longer travel up to E to get both sides. So E to anything else makes sense. Again, if we look at it with the directions, E to anywhere else we can do, okay? But we can't travel backwards along directed edges. All right, so that's the concepts that we take from tree and bring to rooted tree. Now, just a couple of notational things for a rooted tree. So when we're working with a rooted tree, if there's a directed edge from one vertex to another, then we say that U is a parent of that other vertex V, or that V is a child of that other vertex, okay? So essentially what we're looking at here is parent-child. Makes sense. Parent-child, parent-child. But we also have parent-child, parent-child. Okay, so one vertex could be both a child and a parent, and that makes sense, right? I is the child of E, but I is the parent of H. Okay, cool. So what we end up with here is essentially a family tree, and this is exactly the sort of language that we use, but of course we're looking at it growing downwards here instead of like most family trees growing up. But this makes sense, I think, as well. All right, so the vertices other than V on the directed simple path from the root to V are called the ancestors of V. And V is a descendant of its ancestors. So if we wanted to up here, we could say, look, the ancestors of F are B and E. Cool. We could also say the descendants of B are F, C, G, and J. Also, cool. All right, so a terminal vertex, and this isn't necessarily anything new. It doesn't quite fit within the idea of the family tree, but a terminal vertex is simply a vertex that has no children, so given in the language of the family tree though. And an internal vertex is one that does have children. So here at the ends, terminal, 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 and everyone else has children, so they are all called internal vertices. Excellent. And that's all that I wanted to share for this video. In our next video, we'll take a look at an example identifying roots, internal, terminal, parents, children, descendants, ancestors, that sort of a thing. And then we'll also look at rooted trees as a way to find partitions. So a couple more videos with a couple of examples. So I'll see you guys back in the workshop very soon.